In the enduring human pursuit to find life beyond our planet, a remarkable discovery has reshaped our entire understanding. Picture a world that is not only able to support life, but might even exceed Earth in its capacity to do so. The James Webb Space Telescope, an extraordinary symbol of scientific progress, has identified a new planet, and the calculated likelihood that life exists there, a staggering 99.7%. This is not mere speculation. It is a figure derived from careful analysis, grounded in extensive scientific evidence, and obtained through the most advanced observational instrument humanity has ever developed. The world detected by James Webb is a place where life could have developed in forms far beyond anything we have ever imagined. This planet is K218b, and in this exploration, we will examine the data, the reasoning, and the remarkable evidence that supports this astonishing probability. Could there come a time when we are able to communicate with beings from this world? What forms might such life take? And above all, what implications does this discovery hold for the future of humanity? Get ready, because what lies ahead may permanently alter your understanding of your position in the cosmos. This is not fiction, this is reality, and it is unfolding right now. K218b belongs to the K218 stellar system, where it revolves around a red dwarf star bearing the same designation, positioned deep within the constellation. Leo K218b lies roughly 120 light-years from Earth. On a cosmic scale, this distance is relatively modest, providing astronomers with a valuable opportunity to perform more thorough and detailed investigations that go beyond the typical constraints of studying faraway celestial objects. In terms of its physical characteristics, K218b stands out as an extraordinary planet, with a radius about 2.6 times that of Earth and a mass approximately 6 times greater. It falls into the category of either a super-Earth or a mini-Neptune. This considerable size is not merely a statistic, it offers meaningful insights into the planet's nature. A body with such mass and radius is likely capable of holding onto a dense atmosphere, a crucial element when evaluating its potential to support life. This atmosphere not only functions as a protective shield, but also creates a setting where complex chemical interactions can take place. Setting the stage for possible biological discoveries, K218b was first identified in 2015 by NASA's Kepler Space Telescope. Kepler represented a groundbreaking mission specifically engineered to detect exoplanets by observing subtle decreases in a star's brightness as a planet crosses in front of it. Through this technique, Kepler was able to detect K218b. It verified the presence of a planet within the K218 system and established K218b as a promising candidate for more advanced research in the future. In 2017, the Spitzer Space Telescope contributed significantly. Data gathered by Spitzer helped confirm that K218b resides within the habitable zone of its parent star, K218. This marked a critical advancement, elevating K218b from a simple exoplanet detection to a highly compelling target in the search for life. 2 years later, in 2019, the Hubble Space Telescope delivered a major breakthrough through its advanced spectroscopic instruments. During observations of K218b as it transited its host star, Hubble detected the presence of water vapor in the planet's atmosphere. This represented the first indication of a life-supporting substance on this world. The launch of the James Webb Space Telescope in 2021 ushered in a new chapter in astronomy, particularly in the study of exoplanets. Equipped with unprecedented infrared sensitivity and far greater observational power than its predecessors, James Webb was expected to reveal deeper details about the atmospheric composition of distant worlds. K218b, already showing promising signs from Hubble and Spitzer, quickly became one of its priority targets. In 2023, scientists obtained and examined detailed atmospheric spectra of K218b. What began as curiosity soon turned into astonishment. Within the atmospheric data of exoplanet K218b, researchers identified a strong signature of dimethyl sulfide. This is an extraordinary organic compound. What makes this finding especially remarkable is that, on Earth, DMS is mainly produced through biological processes, particularly by marine phytoplankton. Its detection on a planet 120 light-years away presents a compelling signal, one that demands serious attention. Alongside dimethyl sulfide, scientists also observed elevated levels of methane and carbon dioxide. The coexistence of dimethyl sulfide, methane, and carbon dioxide paints a picture suggestive of possible life, perhaps not identical to Earth's life, but life nonetheless. Such chemical imbalances, where compatible substances persist together longer than expected, often indicate ongoing biological activity operating beneath the surface. Much like the story of Goldilocks, K218b may exist within a zone that is just right for life. Not excessively hot, not excessively cold, allowing liquid water to remain stable. This concept moves far beyond traditional expectations of life. If life has indeed developed under the extreme and unfamiliar conditions of a Haitian world like K218b, could intelligence emerge as well? A form of life capable of learning, adapting, and shaping its surroundings? And could it follow a completely different evolutionary route from the one taken on Earth? On our planet, human intelligence has been influenced by our ability to use tools, communicate in complex ways, and move across land environments. But on a world covered by a global ocean with pressures hundreds of times greater, no solid surface, and near total darkness, the evolutionary framework would be fundamentally different. Conventional technologies such as metallurgy, construction, and fire would not be possible. Even on Earth, we already observe hints of alternative strategies, organisms that form symbiotic relationships or regulate small ecosystems in order to survive. If such processes were taken further, an intelligent species might develop or manage microbiomes to perform specific functions, essentially creating a form of organic, living technology. However, what is most striking about K218b is that it compels us to broaden our understanding of where life can arise. In the past, astrobiology concentrated almost entirely on rocky, Earth-like planets, where sunlight could sustain living systems. Ocean-covered planets and worlds, once dismissed as improbable candidates, are now taking center stage in scientific investigation. If intelligent life is capable of arising without land, without fire, then our most basic assumptions must be carefully reconsidered. One essential element that gives K218b such remarkable promise is the nature of its host star. K218b circles a red dwarf, a class of star known for lifetimes extending hundreds of billions of years, vastly exceeding that of our Sun. This prolonged duration provides a significantly expanded window for evolution, allowing life, if it is present, ample time to progress from simple single-celled forms to complex, intelligent organisms. Yet, red dwarfs are not without difficulties. They are known to produce intense magnetic flares, powerful enough to erode the atmospheres of nearby planets. However, the dense hydrogen-rich layer surrounding a Hycean world like K218b could serve as a protective barrier, helping maintain the atmospheric stability necessary for life to thrive. Human technology depends on fire, metallurgy, and solid ground. But on an ocean-dominated planet, where combustion cannot occur, where no dry land exists, and where immense pressure governs the environment, our familiar version of technological development becomes impossible. This reality forces us to imagine entirely different evolutionary pathways for intelligent beings. Water, with its distinctive chemical and physical properties, is not only the basis of life as we understand it, but also a central component in every biological process. Its extraordinary capacity to dissolve substances makes it the universal solvent, enabling the movement and interaction of nutrients. In a vast ocean, where sunlight struggles to penetrate the depths, photosynthesis, as we know it, driven by light, may either not occur or be confined to the very upper layers where faint light still reaches. On Earth, communication relies heavily on light and sound. However, in deep aquatic environments, light is quickly absorbed and becomes ineffective beyond a certain depth. In contrast, sound travels much more efficiently in water than in air, especially at lower frequencies. For this reason, if intelligent marine life exists on K218b, it may have developed an advanced communication system based on acoustic signals, similar to how dolphins and whales use sonar and long-distance calls for navigation and communication. A sufficiently advanced intelligence could refine these sound-based signals into a structured, meaningful, and highly complex language capable of conveying detailed information and preserving accumulated knowledge. At present, there is no scientific confirmation of life on K218b. Even so, this world serves as a powerful reminder. If intelligence does exist elsewhere in the universe, it may take forms far beyond anything we have imagined. It could vibrate through unfamiliar frequencies, emit faint glows within dark oceans, or communicate through subtle electromagnetic signals. We do not yet know, but now we have reason to search. Beneath the endless ocean of a distant planet, life may already exist, silently observing or patiently waiting to be discovered. To begin with, K218b possesses three fundamental traits that Earth also has, conditions considered essential for the origin and development of life. First, the presence of water vapor in its atmosphere, initially identified by the Hubble Space Telescope and later examined in greater detail by the James Webb Space Telescope. This strongly suggests that liquid water could exist on the planet. K218b orbits its star within the habitable zone, where temperatures may allow water to remain in liquid form. This is a crucial factor, ensuring the planet is neither so hot that water evaporates completely, nor so cold that it remains permanently frozen. The planet's large size provides sufficient gravity to hold onto a thick atmosphere. Such a dense atmosphere functions like a thermal blanket, protecting the surface from intense cosmic radiation while helping to regulate temperature, reducing extreme differences between day and night. Geological processes, including plate tectonics and volcanic activity, play an essential role in sustaining the carbon cycle, a key system that stabilizes climate and supplies vital elements for life. A planet with long-lasting and stable geological activity could maintain life-supporting conditions over extended periods. But the most remarkable aspect is this: K2-18b may be a Hysian world. The concept of a Hysian planet is relatively recent in planetary science. Introduced in 2021, if K2-18b truly belongs to this category, as current models indicate, then its environment might even be more stable than Earth's, which has experienced significant climate fluctuations, including ice ages and major geological transitions. This kind of long-term stability could be a crucial factor, allowing life to evolve continuously without major interruptions. When we evaluate other possible candidates, what makes K2-18b so exceptional? The value of 99.7% probability of life is not based on mere speculation. It arises from advanced statistical analysis using Bayesian algorithms, an approach that measures likelihoods according to existing evidence and refines them as new information is obtained. Combined, these elements create the most robust probability model ever established for a potentially habitable exoplanet. Nevertheless, true scientific rigor always acknowledges uncertainty, which is why the value never reaches 100%. Even at 99.7%, there remains a 0.3% margin of uncertainty. This does not reflect hesitation, but rather adherence to the principles of empirical science. Until direct observation is achieved or a physical sample is obtained, all conclusions remain grounded in statistical inference. There could still be an unknown geological or chemical mechanism capable of generating dimethyl sulfide without the presence of life. And perhaps even more significant is the Fermi paradox. If intelligent beings exist elsewhere, why have we not encountered them? Yet within astronomy and astrobiology, a probability of 99.7% is extraordinary. It is more than just a figure. It acts as a beacon, guiding technological development and investment. It explains why organizations such as NASA, ESA, and CSA continue to prioritize the observation and study of K2-18b. The identification of K2-18b and its possible biosignatures is not merely a scientific achievement. It holds profound implications, transforming how we perceive life beyond Earth and redefining humanity's place within the universe. This represents a pivotal step forward, taking us beyond theoretical assumptions into the domain of observable evidence. If K2-18b indeed supports life, it will fundamentally shape the direction of future missions dedicated to the search for life. K2-18b, with its strong indications of potential biosignatures, stands as a historic milestone in the search for extraterrestrial organisms. However, the journey is far from complete. What we currently observe on K2-18b are only preliminary indications that must be verified and examined more thoroughly. Science is an ongoing process of inquiry, data gathering, and hypothesis formation. For this reason, we must continue to follow scientific progress, support space exploration initiatives, and maintain our sense of wonder about the vast cosmos. The universe still contains countless mysteries waiting to be revealed. K2-18b is only the starting point, and with each new discovery, we move closer to uncovering the deepest secrets of the cosmos.